video, we're going to learn how to use the Laplace transform to solve an initial value problem. But first, we have to get familiar with the theorem that tells us how to find the Laplace transform of a derivative. So according to this theorem, a function f and its derivatives up to n-1 order are continuous on the interval from 0 to infinity, including 0, and are of exponential order. And if the nth derivative of the function f is piecewise continuous on that same interval, then this is how we're going to find the Laplace transform of the nth derivative of function f. Let's try to understand what is what here. So once again, here n represents nth order derivative. This is what it equals to. S to the power n. So s is that new variable that we obtain after we perform Laplace transform, and then n in this case represents the power. Notice this power matches the order of the derivative. Now s is the variable, so it's s raised to the power n. Now what is uppercase f of s? Well, that's the Laplace transform of the function f. So here we're performing Laplace transform of the nth derivative. But f of s here is the Laplace transform of function f. And next we need to subtract terms that consist of the following. So it's a product of, again, variable s raised to the power that's being reduced by 1 in each term from power n down to power 0. And that is being multiplied by f of 0, so function f being evaluated at 0, f prime evaluated at 0, and so on and so forth up to the n-1 derivative evaluated at 0. So if we try to generalize this expression, we can see that all terms have s raised to the power that starts with n and then continues in the descending order. And then the first term has Laplace transform of function f, and after that we have, well, function f itself evaluated at 0, and then derivatives of f in the increasing order up to n-1 derivative, and they all are being evaluated at 0. Well, let's try to apply this formula, this definition, to a few cases. For example, what is Laplace transform of the third derivative of function f? Let's follow this pattern. So we start with the first term will contain s to the power that's same as the order of the derivative, so it should be s to the third power. Then we have to multiply it by the Laplace transform of f. Now, one way is to use the uppercase f, or you can use the Laplace transform notation. It's Laplace transform of f of t. Like that. That's the first term. Next, and then we start subtracting terms. Next one will have also s raised to the power that's 1 less, so that's going to be s squared, and it's just function f evaluated at 0. Minus, then I will keep reducing power of s, so it's going to be s to the power 1, which is just s, and then here I am starting to increase derivative, so it's the first derivative, and as I do next term, that's going to be last term. While power of s here will be 0, here was 1, now it's power 0, well, s to the power 0 is just 1, I don't have to write it, but then order of the derivative goes up by 1, so it's the second order evaluated at 0, and that's where we stop. So we stop when we get down to power 0 for s, and when we get up to the order of the derivative that's 1 less than the original one. So that's how the Laplace transform of the third derivative is performed. Of course, this is all written in general form. How about Laplace transform of the second derivative? Well, we start with s raised to the second power. That should match the order, right? Then times Laplace transform of the function f, that's always in the first term, and then minus, so I reduce the power of s by 1, so just s to the first power, which is just s, and then f of 0 times f of 0, minus, reduce power of s by 1, that becomes power 0, s to the power 0 is 1, I'm not going to write it, but then I have to multiply it by the first derivative of f, so f prime of 0, and that's where we stop. And finally, Laplace transform of the first derivative is s to the power that matches the order, which is 1. So s to the power 1 times the Laplace transform of the function f minus reduce power of s by 1, so that becomes s to the power 0, which I will not write, and times f, function f evaluated at 0. And then we stop for the Laplace transform of the first derivative. So that's how we find Laplace transform of the first three derivatives. And that is something that we'll need to solve the initial value problem using the Laplace transform. Let's do an example and see what steps we have to take. So use the Laplace transform to solve an IVP, and here's the initial value problem. As you can see, it's a homogeneous differential equation, and these are the initial conditions. So solution to this initial value problem will be a function that satisfies this differential equation and those two conditions. Let's write down the steps. So we start by applying the Laplace transform to both sides of the equation. But we know that since the Laplace transform is the linear operator, when we apply Laplace transform to sum or difference, it's the same as applying Laplace transform to each term of that sum or difference. So for that reason, I'm going to write step 1 this way. I'll say in step 1, we need to take the transform of each term of the equation. And of course, we have to do it on both sides. So that's how it's going to look like. So the Laplace transform of the first term, y prime, minus the Laplace transform of the second term, 6y prime, plus the Laplace transform of the third term, 13y. And of course, I need to do it on the right-hand side. So Laplace transform of 0. Next, I'm going to use the linear property of the Laplace transform that says that if we have a constant coefficient in the Laplace transform, that coefficient can be put outside in the front of the Laplace transform. And I will also use different colors so it's easier to understand how I'm going to perform substitution in the following step. Okay, so the first one, I don't really have a coefficient here, so it's just copying that down. Then minus, okay, so that coefficient 6 I'm placing in the front, so that's going to be minus 6, the Laplace transform of y prime, and then plus, again, this coefficient 13 I'm placing in the front, so plus 13, the Laplace transform of y, and the Laplace transform of 0 is 0, so the right-hand side is 0, like that. So what we're going to do next, we're going to expand each Laplace transform of a derivative according to the definition that we just learned. So we just learned that the Laplace transform of the second derivative, and we already practiced expanding it right here, equals the following. So the only difference is that our function is called y instead of f. So it means that in our case, it's going to be s squared, the Laplace transform of y, minus s y of 0, minus y prime of 0. And that's what I'm going to replace the Laplace transform of the second derivative. Okay, here we go. So it's s squared, the Laplace transform of y, minus s y of 0, minus y prime of 0. That's what the Laplace of the second derivative is. Minus 6, and now the Laplace transform of the first derivative, I am also replacing with what it equals to. Now we have this coefficient 6 in the front, so that means that the result of this Laplace transform I am putting inside the brackets. And let me remind you what it equals to. So the Laplace transform of the first derivative is here. Instead of f, I'm using y, so it's going to be s Laplace transform of y minus y of 0. Okay, so it's s, the Laplace transform of y minus y of 0, like that. And, well, the last term here is just the Laplace transform plus 13, the Laplace transform of y. I'll just keeping it like that for now, equals 0. So this is what we get if we take the transform of each term of this equation on both sides. What do we do next? Next, our goal is to solve this equation for the Laplace transform of y. So notice we have the Laplace transform of y here, here, and over here. So our goal is to solve for that. And there are a couple of things that we can do to help us. So first, we need to remember that that was the initial value problem that we were solving, right? And we were given the initial conditions. We were given y of 0 equals 0 and y prime of 0 equals -3. Wow, look at what we got now. See how we have y of 0 here? And we know what that equals to. So y of 0 equals that equals 0. And then y prime of 0, so that part, equals -3, according to the initial conditions. Now right here, y of 0 equals 0. Well, that means that those two terms are gone, right? This one is gone and that one is gone. But that one we will replace with -3. What else do we need to do to help us to solve for Laplace transform of y? Well, we would definitely want to distribute at -6. So let's do all that. Now I'm going to be back to one color. So the first term is s squared, the Laplace transform of y. Now that term is gone. Now here I have -3, so it's going to be +3. I'm distributing -6, so I'll have -6 as the Laplace transform of y. Now this term is gone. It's 0, right? So I don't have anything else here. So then I'll have to continue and say +13, the Laplace transform of y equals 0, like that. So now it looks simpler than it used to be. And do you see how we can solve for the Laplace transform? What we do, we just combine all terms that involve the Laplace transform of y. We're going to factor out the Laplace transform out of all those terms, and we also have term +3 that's not like term. So we're going to subtract 3 so it appears on the right hand side, and on the left hand side, among what we left, we're going to factor out the Laplace transform of y. Let's see what's going to be left from each term. So if I factor out the Laplace transform here, I'm going to have left s squared. From here, we're going to have -6s. From here, we're going to have +13. And we already talked about how we're going to subtract 3 from each side. So that means that I have -3 on the right hand side. Okay, and now to solve for the Laplace transform, we just have to divide both sides by this trinomial. So the Laplace transform of y equals -3 over this trinomial s squared minus 6s plus 13. And let me add the step. We didn't write the description of the step, so it's going to be step 2, solve for the Laplace transform of y. I'm going to write it over here. Okay, so here it is. I inserted the description of the second step. So technically we only have one step left, and this step is the following. Well, remember, we're solving the IVP, the initial value problem, and we said that we had to find a function y, such that it satisfies equation and it satisfies the initial conditions. Well, what we found so far, we found the transform of function y. So if you apply Laplace transform to function y, that's what we're going to get. But what is function y itself? How do we find it? Well, for that we just have to apply the inverse transform, right? If that's the result of Laplace transform, well, once we apply the inverse transform to this, then we're going to obtain function y. So let's say use the inverse transform to find y. Once again, to find function y, we're going to apply the inverse Laplace transform to the following function, -3 over s squared minus 6s plus 13. So to find the inverse transform, we usually use the table of Laplace transforms. Well, here it is. And our goal is to find in the table, in the right-hand side column, to find expression that resembles the function that we have. And if you look at the table, you're not going to find a function with the quadratic trinomial in the denominator. And there are a couple approaches that we can take to rewrite this function in a different form. One of them is partial fraction decomposition, and the second approach to complete the square in the denominator. Now, as I look at this trinomial, I can see that I can't really factor that easily. So with numbers -6 and 13 here, I cannot factor in my head. And because of that, I'm not going to go with the partial fractions decomposition method. I'm going to use the completion the square method. So this is how I'm going to write it, the inverse transform. Now in the denominator, I'll write s squared minus 6s, those two terms. Well, I have to add 9, so it's a complete square, right? Remember, it's half of that middle coefficient squared, so half of that is -3. -3 squared is 9, so that's the number I need to complete the square. But I had 13, so it means that I need to add 4 more, so altogether I have exactly the same expression that I started with. Okay, so now I can rewrite it in the form s minus 3 squared plus 4. And now this is starting to resemble one of the expressions from the table. Let me show which one. Okay, so it's down here in my table. I have actually two expressions that, as far as the denominator, they look very closely to what I have. So it's s minus a is the constant, while k is also a constant, so variable s minus a constant, all that raised to the second power, I have that part, and then plus constant, some kind of constant squared. I have 4 and definitely can represent as 2 squared. Okay, I have that. And then in the numerator, there are different numerators. So one has just a constant and the other one has a variable s minus a constant. Well, obviously I don't have any variables in the numerator, so I'm going to go with this expression. The only thing I have to make sure is that numerator, that constant in the numerator, is the same one that's being squared in the denominator. And as I can see here, it's not. So in the denominator, I have 4, which is 2 squared, which means that k equals 2, or should be 2 for me. But then in the denominator, I have -3. Well, I'll do the following to fix that. I'm going to multiply by 2, well, because I do want to have 2. And then to make sure that my expression stays the same, I'm going to write next to it, multiply by 1/2. So let's say I put it here, times 1/2. And with those two operations, well, I'm multiplying by 1, so I'm not really changing anything. And what I'll do in the next step is the following. I only need 2 in the numerator. I don't need that -3, and I don't need that 1/2. So I'm going to put them together, and since it's just a constant coefficient, I'm going to place it in the front of the Laplace of the inverse transform. So that's what I'll get. So -3 over 2, that's that combined with 1/2. -3 combined with 1/2. -3 over 2. I am placing in the front of the Laplace transform, and my expression now looks like that. I have 2 in the numerator, then s minus 3 squared plus, well, I'll keep it as 2 squared in the denominator. So it's easier for me to see what is what. Okay, so once again, k is 2, and then here, that's what we call, or that's what it's called, a in my table. And now that helps me to put everything together and write down the result of this inverse transform. So that is the result. So let me write that down. So I still have -3 over 2 in the front, and then the result of that inverse transform, where is it? Right here. It's e to the power a t, so it's e to the power a. A is 3t, and then times sine of k times t. K is 2, so it's 2t. And that's going to be the solution. This is what y equals to. Remember, that's how we had to find y, and we obtained it. So solution to this initial value problem is y equals -3 over 2, a to the power 3t sine of 2t. And if you use one of the old approaches, let's say if you use characteristic equation to solve that initial value problem, then that would be a good way to verify the solution using different method. Now, as we recap the steps that we have to take to solve this initial value problem, then remember we started by taking the transform of each term of that equation on both sides, of course. Then we wrote what the Laplace transform of the second and first derivatives are, right here. So all that had to be simplified and cleaned up so that eventually we can solve for the Laplace transform of y. And once we know what that transform equals to, then we can use the inverse transform to find function y itself. And these are the steps, and again, that's the solution that we got.